Hello, this is a video covering Chapter 2, which is titled Strain. This is from the Hibbler's Mechanics of Materials text for the EGR 305 course. Now, this particular chapter is pretty small, so I suggest you go through and read the chapter. It's only 4 pages. I suggest you go through and read it before going through this video. This kind of just highlights some of the important features of the chapter. And the concepts are pretty quick, but it's more going to be about geometry. So this chapter is really going to be about geometry, or really what happens when a material deforms. Okay, how do we analyze that deformation? And we call that strain. The first part of the chapter shows 2 pictures, right? This is rubber, or some sort of rubber material that's very easy to deform, and they took a machine and they pulled this apart. So this, I tried to change each size of the images here, but this distance here is larger than this distance, right? And this would be kind of my unloaded, or maybe an undeformed case, and this would be a deformed and a loaded case below. Right? So here we take a rubber band and we have some drawings on there, and then we stretch that rubber band and we see that the lines change in their size. This particular line right here, the long one that's drawn down the center, that line sees the greatest change, right? Because it's aligned with where we are pulling the material. This horizontal line will also see a change in length, right? But probably not as drastic as this line that's drawn down the middle. And then this horizontal line is probably not going to change much at all in length. It may actually thicken up, right? But it's here to illustrate that deformation is going to occur in different directions, right? So it's very dependent on which direction you're kind of placing yourself, right? And what we can do with this deformation, we can categorize this deformation and identify how this deformation is going to take place throughout a material. And I identify it from an engineering perspective using dimensionless quantity strain. Okay, this is the value you're going to be using to define deformation of material. This other picture here to the right is not one in this part of the text, but we're going to see it a little bit longer, or in the next section. And this shows that deformation, or this strain, can change throughout the body, right? In this particular case, this is ductile failure, failure of a ductile material, where you can see the original diameter back here, right, is larger than the original, or than the diameter that's seen right before this particular material was breaking, right? That is what we call necking, right? And this becomes a case we're going to see for material deformation when we see strain hardening, okay? So strain is kind of our engineering term that is a measure of deformation in a material. Now, homework for Chapter 2. The homework will be due on the 12th. Scan it in and turn it in D12. This should be in your syllabus, these 3 problems here. I'll be picking from one of these problems on the 10th for somebody to present on the board, and this actually here doesn't make any sense because we're going to be going over this on the video. So make sure to complete this homework and read through this, or watch this video and read through the chapter before next week. All right. Okay. So normal strain, section 2.2. At 2.1, the big takeaway there is the idea of deformation occurs. Whether it can occur in several different ways, but the 2 primary ones we're going to consider in this text are if you have a loaded, unloaded, right? So this is like a loaded axial member, right? But the other case where you might see is with a thermal deformation, right? If you heat up a material, it's going to tend to expand. So you might see a strain that occurs from that as well. So the term strain is referring to Greek letter epsilon. Here we're saying the average strain is L, which we get from the new, or this is our kind of deformed case, right? Our deformed length over our undeformed length I'm having trouble writing this word. I'm going to erase that and start over. Forgive me, I'm using a tablet here. And so I'm going to write, this is undeformed. Okay, so this is an undeformed length L naught, right? And we're referring to the deformed length L, okay? And then really the main difference here is our Greek letter delta, right? So delta is equal to the deformation, right? So the change in original length. So when we speak about strain, we're not referring to its deformation. We are in fact referring to its epsilon. And I'll tend to write epsilon as kind of a backwards 3, because that's a little bit easier to see than the epsilon from the text. And we call this average strain because we're averaging the strain over the entire body, right? We're kind of ignoring what the strain might be at any given location, right? And just saying that the strain is going to be the same, right? If we were to take small bits of elements and measure those changes, right? This would be the average strain. Okay. Now, if we wanted to get more accurate, so say, for instance, the loading was more complex, we may want to shrink this down. So we can take the same idea, right, and take it to between 2 points on a body, right? So we have our undeformed case here, or an unloaded case, where we take these 2 parts that are separate by a straight line, and then when we load it and it reaches equilibrium, we have a deformed case, and this value will be different, okay? So here, delta S prime, this is our deformed case, and then this would be delta S is our undeformed case. So each of this idea of strain, but for both normal and subsequently shear strain, you're taking an original dimension, right, when it was not loaded, and then you're adding the load in, and then you're seeing how much that material changes. And the reason why this is a limit as delta S goes to 0 is because this is not an average strain, it's a strain at a point, right? So strain as delta S goes to 0, right? All these terms will go to 0, but the ratio of those terms do not go to 0, okay? And so that's it. That's really for normal strain. Those are the cases that we see there. This is only strain that's going in a normal direction, normal to a surface. So the 2 questions I would ask are what are the units of strain? And you should be able to see that here, right? So here, if we were looking at this, units of length over units of length. And that might seem trivial, but strain itself is dimensionless, okay? Sometimes you might see epsilon is given as some value like 480. And these are going to be very small values, 10 to the minus 6 here. And this, you might see this given as inch per inch, okay? Meaning those lengths will cancel each other out. This is the same as saying 480, 10 to the minus 6 meters per meter. Same exact thing, right? Because these units cancel each other out. And the reason why we wrote this way is because it could say 480 micrometers per meter, okay? And then the last one I'll write out here, 480 micros. So sometimes this is a common way you might see it. These are all the same, okay, for epsilon or given value for epsilon. But this is kind of helps you out to write this in kind of a manageable form. And these are going to be kind of values you're going to see in your problems, right? So the real answer for, what are the units of strain? You just say they're dimensionless, right? Can strain be negative? Well, of course, yes, it can. Okay. If in both of these cases, we're showing kind of a load under tension, right? These are kind of under tension. So under tension, we have the delta S prime, which is our loaded, this is our loaded case, right, is going to be larger than the delta S that we started off from, right? And this means epsilon will be positive, right? Under compression, our delta S prime will be smaller than their original size, right? Because we kind of switch the direction of these arrows coming in, and then we want to compress this. So then epsilon will be negative. So yes, epsilon can be positive or negative. In fact, it's really important to notice that there will be a difference there. Okay, and this comes back to relating it to its original distance or its original change. Okay, so that's for normal strain. Shear strain, which is given by the Greek letter gamma. Okay, this is gamma here. That's equal to some original angle, pi over 2. This would be like our undeformed case, minus this new angle, which represents our deformed case. So this is undeformed, and this would be deformed. And this is illustrated above here, right? So if we start off with our undeformed body, this is no load, right? We draw a 90-degree angle edge here. And if we were to take a look at this edge, depending on which direction we have for strain or the shear stress or shear force, right? The shear stress through the body is going to change that angle. And this kind of seen here, right? So if we kind of think of this as like a deck of cards, right? All the material, the top of the material is going to want to go to one side, or the top of the material is going to want to go to the other side. And each of these cases, the original angle is going to look a little different. Here, theta is going to become less than 90 degrees, right? And here that means gamma will be positive, right? Because theta is less than 90. And in here, theta is larger than 90 degrees, so that means gamma will be negative. Okay, and so I like these illustrations here, right? This is our new angle, theta, and then the remaining angle, kind of from the 90 degrees, that is our gamma. So this is typically given in radians, right? Gamma is given in radians, which are dimensionless by nature, okay? It's a measure of angle. Okay, so gamma is always given by radians, and it can be positive or negative. Gamma you can also see it on this one here, where the theta, when it's larger than 90 degrees, right, where gamma is here. Here we refer to gamma as being negative, right? And it all comes back to this relationship here, where it's equal to pi over 2 minus theta. Okay, so it's important to remember the convention here for negative and positive. If we take a look at an element in Cartesian coordinate systems, if I take a little piece of my potato, right, and I zoom in on that, whenever we're measuring strain, we always start with an undeformed case, an unloaded case, and then we go to the deformed case, right? And this would represent the most complex type of change here. It may not always look like this, right? Where you have your normal strains here, epsilon z, epsilon y, and epsilon x. And then you have your shear strains, gamma xz, gamma xy, and gamma yz, right? And the reason why they're calling this is that this is kind of our new length, right? So it's like saying, for looking at the delta z case, it's like saying delta z prime should be equal to 1 plus epsilon z times delta z, right? Its original length. This is just reformatting the equation we saw for engineering strain in the previous page. And then for gamma, right, we know our definition for gamma is equal to pi over 2 minus theta. Well, I can rewrite this in saying theta is then equal to pi over 2 minus gamma, right? And that's why we see it in this form here. But the overall takeaway here is that normal strains are going to cause a change in the volume. Okay, so if there's no shear strain at all, it would just change the sides of this cube, right? So it changes these sides, whether it changes it to make it larger or smaller. It just makes a change in volume. Shear strains will cause a change in shape, right? Because it's changing these angles that you see here, right? So here, that's how these two are combined. And a lot of time when we're looking at this case, this is the evidence, right? So strain is the evidence. Okay, strain is the evidence of some case, whether it's usually some development of stress. Stress is what's causing strain. We can't measure stress, but we can sure measure strain. right? So one of the things that are going to help out for this section are remembering some trigonometric properties. Okay, the big one here is law of cosines. Okay, and the way I remember this is if I'm trying to find this value right here, I can take the opposite 2 squared, right? And then minus 2 times AB times the cosine of this opposite angle here. So law of cosines are used when we know these 3 quantities. And it can be done in any position, right? So I can do this with A as well, if I knew B, C, and alpha. And same thing with B, if I knew A, or beta, and C. Law of sines are helpful for when we know the A and the opposite angle, or the length of one side and its opposite angle. We can combine that to look, and if we know the other terms here, we can either find the angle or the length of the other parts of the triangles. So a lot of these problems are going to be set up, they're kind of 2D planar plot problems, or we would, if it's in 3-dimension, we would just look at a two-dimensional part of it while trying to measure out strain. Okay, so let's take a look at an example in the text. So this example is saying if we have a force applied at C, right, and this force here, P, causes this arm to rotate down such that this angle that it changes through, right, this angle will then be, for its new position, it's going to be 0.05 degrees, okay? So let's think about what that really is. That this here is not, it's not gamma, right? That we're not looking at, we're just looking at this rigid body, right? I think does it say, it says rigid, yep, this is a rigid lever arm, ABC, and it rotates counterclockwise about pin A for 0.05 degrees, okay? And then it says determine the normal strain, so this is a normal strain problem, that is developed in wire BD. So it stands to reason if this thing, you know, is turning at an angle. Now this is of course highly exaggerated, right? That this length of BD is going to increase, right? And it's going to increase at a very small value. This is a very small angle. Now one of the things I should have said before, and I missed out when coming back into the trigonometric solutions, is this idea of small strain analysis. Okay, in this class, get this back. In this class, we are going to be only working with very small deformations. So we can assume small angle approximations, meaning if I have a very small angle, right, if I say my angle theta is much less than, I believe the textbook goes over, it's much less than, or it doesn't say the angle is much less than any sort of value. Maybe I should rewrite this. The textbook specifically says that if we are working with very small values of strain, right, if strain or shear strain are much less than 1, we can use this idea of small strain analysis, where it says if we have a change in angle, right, delta, get rid of this, not delta S, delta theta is really small, then we could say the sine of delta theta should just be equal to delta theta, right? And this is kind of our small angle approximation. Cosine of delta theta will be equal to 1, and then the tan of delta theta will be equal to delta theta, okay? This is kind of our small strain analysis, and you can use this to get good measure of what's going on. This comes from trigonometry here. So looking back at this, these are going to be small values, right? So I've got this thing already set up here. So this is our picture. I'm going to redraw out our picture saying that in its deformed case, right, we have something that would look like this, right? This would be kind of like its original position. This would be position A. This would be position B prime. This would be position B. And this would be position D, right? So the unknown here, the unknown quantity, is it's looking for the, let's go back to this previous slide, it's determining the normal strain, right? So we're trying to find epsilon BD, right? Which epsilon BD should be equal to LBD prime minus LBD over LBD, right? Because LBD would be the original length. Okay, so we already know LBD is given to us by the problem, 300 millimeters, right? Now we just need to really find this, I guess we can call this LB B prime, which is right here, if we knew that this angle here is given to us 0.05 degrees, right? So we can do this a few different ways, right? One way is to use law of cosines, okay? Now we could find this angle because we said that this dimension here is 400 millimeters. This dimension here is 300 millimeters, right? All the way to B, right? It's like its original deformed shape. And so by relations, this is a 3, 4, 5 triangle, right? So this would be 500 millimeters, okay? If you needed to use Pythagorean to figure that out, that's fine. So we can find this angle, and I want to call it theta, but maybe I'll call this beta, right? I can find beta here by just saying, I don't even need to know this 500. I can say the beta should be equal to the inverse tan of 300 millimeters divided by 400 millimeters. And I've got my calculator right here. I'll do that real quick. And that gives beta is then equal to 36 point, I guess I'll just say 36.9 degrees, right? Which I believe is the same, is really for the 3, 4, 5 triangle. The angle that I always remember is 53.1, right? So that's opposite of that value. So if we want to use law of cosines here, right? dB prime, this quantity should be equal to the squared quantity of this value, right? Which is still 400, right? So we're trying to find not the 300, right? We're trying to find this B, D to B. So we need this value here and this value here. We said 500, right? So it'd be 400 millimeters quantity squared plus 500 millimeters quantity squared minus 2 times 400 millimeters times 500 millimeters, and this quantity multiplied by cosine now of beta plus 0.05, right? So we would say 36.95 degrees, right? Or something, actually I rounded here. Really, I should say that beta should be equal to 36.8698, right? Degrees. So in a sense, this angle should be close to 36.95, but this whole quantity here should be squared, right? So I'm running out of room here. But if you carry through that calculation, that should be 300.3491, and this would be in millimeters, okay? So now we have our LDB prime. We can then plug that into our epsilon calculation. Epsilon BD is then equal to 300.3491 millimeters minus 300 millimeters over 300 millimeters. And then epsilon BD, we get that it is 0.00116. And I would be okay if you just boxed this in. Okay. But you sometimes can put in, and this is given to us, the units are kind of millimeter per millimeter, right? Because that's what's left over. So this is just using law of cosines, but we could have also used kind of a shortcut way, is if we were to kind of use we'd say small angle approximation, right? Where since 0.05 degrees is pretty small, we can say in this distance LB prime can be found by saying, all right, well, the sine of 0.05 degrees should be equal to really just 0.05 degrees, which if we want to calculate that in radians, we'd say divided by 180 times pi. This would make it in radians. So what is that value there? It is 0.05 divided by 180 multiplied by pi. It is 0.008726665. This is very, of course, it's a little too many. It's not that many significant figures. You can write this in scientific notation. But if we wanted to find the LBB prime, that would just be equal to our angle, right? This angle in radians. So 0.000872665 multiplied by, now it's the hypotenuse, right? Which is just 400 millimeters. So this should be equal to, multiplied by 400, that's equal to 0.3491 millimeters. So that's the same, right? This distance here is the same that we see here, except this is just LBB prime. So then LDB prime would then just be equal to 300 plus that, right? So its original size. So that would be 300.3491 millimeters. And then we would wind up getting our same strain, right? So it's two different ways of going about doing this, but it highlights the answer is still the same. Okay, so that does it for chapter 2. Please read through the chapter, complete the homework, and I'll be posting a small quiz on chapter 2 on D2L in a day or so. So thank you, and make sure to email me if you have any questions.